Whatever, my name is Bella, and I'm from Group A. And so first, I'm going to explain the contract. So the contract is the chondrule-bearing meteorite. And
can you briefly explain the Chinese name?
Of Chinese name.
Contract and chondrule.
But I didn't search its Chinese name.
Okay.
Okay.
All right.
I can only explain that it has a unique texture and it is unique to the meteorite. Why it's so unique? Because the elements in the chondrite, it didn't exist on the Earth's surface rock, and it's one from the molten rock, and the molten rock is the temperature is 1,100 degrees Celsius, and we found that it had a similar age to the moon and the Earth, and it also had a similar composition to the sun. And in a solar nebula, there was 3 forms of iron, and one is iron metal, just origin iron. And another one is silicate minerals, olivine, and pyroxene. And these 2 have iron oxide type. And the third one is sulfide, which is iron combined with sulfur. And these 3 iron forms can also find in the chondrite. And with all of this, there is one special one is carbon chondrite, and which means it has a high carbon content and can coexist with the minerals that only stable below 100 degrees, which is the temperature is very low, and more elements can be stored in this carbon chondrite. And non-volatile, which is, should I explain in Chinese? 无易挥发的. So volatile is 挥发的, so non-volatile is, and this kind of element can be stored in this carbon chondrite, and we can refer to the composition in the sun. So this carbon chondrite can give us a link to a solar nebula to the inner planet. So we go back to the figure 5, and first we just in the x-axis is the relative abundance in carbonaceous chondrite, and just we analyze the meteorites from that is then on the Earth, and the y-axis is relative abundance in the sun, which is analyzed by the solar spectrum. And we can find these 2 have a good relationship, a linear relationship. So this can give us an evidence that the elements that is left in the sun atmosphere can give a give a resource to form the Earth's inner planet. So which can show there is a linear relationship between these 2. So this is the end of my talk.
Okay.
Thank you.
Please stay here. Okay. Group A students, we don't have that many students, so it's open to everyone. Students, anyone? Questions? No question? I have a lot. Kevin?
Yes.
Hang on. Hang on. Because I need to record your question.
It's a question. How is the abundance content 5? Because it's a lot of numbers, like 1, 10 square,
10 to the second.
10 to the second, 10 to the 3. And I can't find it. I didn't find it. So
you mean the carbonaceous chondrite or the sun? Which one?
Both of them.
How were they quantified?
Yes.
The x-axis is from the meteorites found on the Earth, and it contains combinations contrast. And I didn't especially search how they analyze the meteorites, but I think it's no more like I don't know if English
Mass
spectrometer. Spectrometer. And the y-axis I searched, I got the answer is from the solar spectrum. They use the spectrum to find a related abundance. Okay? Okay.
Thank you. That's right. Further questions? Questions? No questions? Okay, okay.
So how did the carbon contract form?
How did it? It also it was once melted, and it exists in the sun atmosphere, and 凝结 condense to the sunlight.
Further questions?
Why is the word RE on the graph?
Why is the word on the record spelled
What is REE? Okay, what is REE?
I didn't search it.
Anybody knows that?
I think it's something like reference elements.
No, no. Anybody idea? It's actually very important today. You must have heard during the trade war, 美中贸易战, people are talking about 稀土, rare earth element. That is 稀土. Any questions? No? Cannot. Okay, my turn. Can you go to the slide of contract? Okay, so can you explain us again what is control? Right. More specifically, you say it has a unique texture. So what kind of texture is it exactly? You say it doesn't exist on Earth. How can you tell that?
I didn't read about this.
All right. A group students, anybody know the answer? What is control? It's actually the most important criteria for you to say, okay, it's a meteorite. Otherwise, when you look at a piece of rock, how can you tell it's from the outer space and not from the Earth? Control. A students, now you check this out. Let's see. Kinjun. What is control?
Control is the
Hang on.
control is when the nebula gets cooled and it drops from, and it was once liquid and it's separate from the nebula and then cool down, so it become a rock.
Right. What kind of shape does it have? More specifically, it has a special kind of shape. Control.
Almost split.
Exactly. The mineral is in spherical shape. 它的矿物是圆的. That's the reason why we say you don't find that on Earth. Control. In Chinese, we call this 陨石球力. Therefore, when you heard the Chinese, you probably already know why 球力嘛. Okay, spherical. Alright? That's good. That's my first question. Okay. And my second question is, can you clarify again? What's the you say there's a kind of contrast called carbon contrast, right? And there are also contrasts, which is just contrast. In fact, we call them ordinary contrast, 普通陨石, 普通. Okay, the name contrast in Chinese is 球力陨石. So contour is 陨石球力，就是形容那个形状啊。Contrast is 球力陨石，就是所有有那个形状的陨石都叫球力陨石。Okay, so contrasts, they are ordinary contrasts and carbon contrasts, as you just introduced. So have you read what's the difference and why there's such difference?
Because the carbon contrast have high content of carbon, but the other didn't have.
Why?
Why? From what I remember is the ordinary contrast is their melting temperature is higher, and those volatile elements already disappear. So it cannot like the carbon contrast that contains so many elements inside.
That's good. That's very logical. Yes, although you didn't prepare the slides, but you answered the question very well. So that's the difference. Because the ordinary contrast, can you go to the previous slide? As you, right. You died again. Hello? Oh, okay. Ordinary contrast, it's mineral phase. She just she wrote on the slide 1,100 degrees Celsius. So it's the high temperature mineral phase, which means all the low temperature material is evaporated. Therefore, ordinary contrasts, they were formed in the solar nebula at a hotter zone, 在热区形成的. But the carbon contrast, can you go to the carbon contrast? They have mineral that's stable below low 100, which will be already low temperature. So they were formed, or they accumulate material also at the low temperature zone of the solar nebula, like the outer nebula. And let me think, what kind of question do I still have? Can you go to my question slide? Okay, can you go to the figure? Can you elaborate, which means explain in detail, what does the one-to-one relationship between contrast and sun tell us? You know, they look very different, right? One is very shiny and the other is a piece of rock. So what does that tell us?
It provides the evidence that the inner planetary elements is the resources from the sun.
From the sun.
Mm.
Are you saying that today's sun, the sun is emitting material Out.
No, no.
Are you saying that?
From the start, when the sun forms, from the
We call that
solar nebula.
right.
Okay. And it forms the sun, and it also provides the elements to form the Earth.
Right. Okay. Thank you. That's what I need to hear.
The orbital movement in the solar system. So I want to say it has the.
Can you play the video first? Because the A group, I don't know if they have seen, watched that video. Do you have the video?
I didn't.
Oh. All right.
Maybe.
All right.
So I keep going. Okay. And the first one is the three law of the calendar. And the first one is the orbit of the planet is an ellipse with the sun at one of the 2 points. And the second one is the same area law. And the third one is the constants, the T.
What's T? What?
T 是它的周期。那 R
Period.
是 R 是它的半长度。
Radius.
Radius, yes. And the longer radius. And the third one is the mass of this one is the mass of the host. And
Actually, I don't explain the second.
explain the second.
What's that? Can you read two at least?
A line segment joins the planet and the sun swept out equal area during equal interval. So 它就是等面积定律，同样时间会扫过相同的面积面。然后 then the third one is T is the period and R is the radius, longer radius, and I divide them, they will be a constant. I didn't put this one is the picture. You can tell more easier. And the second law is the same area law. So A1 is equal to the A2. They have the same area and they walk past the same time. And the first law is the orbit of the planet is always in the left. It means it will round and oval shape. And the third one is they have we use the period to divide their radius. There will always be a constant. Okay. And the second question is the density of the planet. And it related to the nebula theory because at the first the sun formed and the sun will have the solar wind, so they will blow all the ice and the gas out of the frost line. So only some like iron and some heavier element still in the frost line. So they form the terrestrial planet. And the out of the frost line will become the gas giant because the gas and the frozen element is more rich. Okay. And third one is the
Can
valuation.
you let us read the density value?
Okay, density. And this is the frost line, and it's also called the ice line. And you can see the gas giant have the bigger volume, but the density is more lower. And the evaluation of the solar system. So The first one is the Sun is the biggest nebula, and they will compress into a single point. So, and beyond a single point, they start to the atom within it became cloudy with increasing frequency, and it convert their K into the heat. So you can know it's around the thing. And the center where most of the mass collect became increasing hotter than the surrounding disk, and become the original sun, the sun nebula.
That's it?
Yes.
Okay. Please stay here. So please open to all. Questions to this presentation? Questions? Okay, Vincent.
Wait. Oh. I have two questions. And my first question is, can you please turn to number 5 slide? Yeah. Can you explain what is difference between density and the corrective density?
Okay.
The density will be always bigger than the corrective density because the density is not in the one bar situation. And if you have more pressures, and your density will become bigger. So the correct density is in the one bar situation. The pressure is one bar. So you have less pressures, and your density will become lower.
Why we don't have a certain value of the corrected density of planets out of the ice line?
I mean, certain density of the ice. We don't have.
Jupiter and Saturn and Uranus, why we don't have a certain value of corrected density?
I didn't read that, but I guess because their mass and their volume is original from the gas, so we can know accuracy.
Do you have answer to your own question?
I remember that in the material it said because the material of these planets is mainly the ice type, and we don't know this material in very high pressure situation, so we cannot correct it. And my second question is, can you turn to number 4 slide? I'm curious that why the planet of gas giant, they if we see the terrestrial planet, the outer planet will be bigger. It means the planet near the sun is the smallest one. But in the gas giant, the gradient it turns to bigger to small. Why?
Because the terrestrial planet they use their form element is a rare element. It's like iron. Iron is very rare in the space, and the gas giants form from hydrogen and helium. So they can easy to catch more gas to become bigger because helium and hydrogen is very rich in the space. And you also have the ice.
Are you satisfied? Or you want to say something about your own question?
In fact, I don't know the answer, but in fact, I want to ask is I didn't remember the name. For example, the blue one, the right hand side, most right hand side, gas giant, is smaller than the orange one, the medium.
Saturn.
Oh, sorry. And why?
Do you have a guess?
I think it's their form because the Jupiter formed the first, so it can collect all the gas in the solar system. So if the second one forms, they don't have the enough gas to form big ones.
My own guess is because it's already big. This is a Saturn. This is Jupiter, and as Saturn is already beyond the frost line. So therefore, if the solar wind blows the volatile contents away, when it's like when the temperature drop below the freezing point, there will be ice precipitating right away. That's my guess. Because it's just beyond, the first planet is beyond the frost line. So, and for the more distant one, they just eat whatever is left from these two giants. That's my guess. Okay. But these are good questions. So, Ethan, shout out loud, please.
The page 3. I want to ask what is the 离心力?
Oh,
why they are so small?
What is eccentricity?
Eccentricity is the definition is the C. The ellipse form have the two. The definition is the 2 point, and we draw a line to their radius, and they 把两点接在一起画一圈，那个长度都是一样的。对，所以我们用它的焦距去除以它的半长度，这是它的离心力，这是它的定义。然后，假如离心力
你可以讲大声一点吗？需要录音。
Eccentricity is more. If the eccentricity is bigger, it means there are more like the depths, and the eccentricity is more lower, and it becomes more like circle. So you can see the Neptune have the biggest eccentricity, so it means their orbit is become more like the depths, not like Earth or Mars. Their eccentricity is small, so their orbit is like a circle.
Okay, thank you. Further question. Okay, Ian, shout out loud. It's not working.
Could you please turn to page 4?
Page 4.
I want to ask is that what is force line and how did it happen? I mean, what factors trigger this force line happen?
What generated the frost line?
I think it's a simple phenomenon because if you farther from the sun, and it will become cold. So frost line is the water can easily to become ice. So the definition is the frost line. And if we have more ice and more gas, and we can form the gas giant. And because the terrestrial planets, their gas and their ice low by the solar wind, so they only remain in some rare element inside the force line. So
Okay. Further question. Question? I need to play. I have some question, but I probably need to play the video clips, and then I need to ask. Okay, so here I said, what is the difference between the orbital movements of the solar system and 10 random balls. So you have to imagine the reference group is 10 random balls. Usually, if you have 10 random balls, then you should be like this, right? There's no reason for the 10 random balls to move in a specific pattern. So you need to ask why, what created the pattern. And first you need to identify what is that pattern. Okay, you see, there is a pattern. So, Ray, could you, I know you answered this question with some, to me it's a little bit more complicated, right? So, can you just look at this video and tell us what's the pattern between these balls and 10 random balls that just found each other randomly? What's the pattern here?
I think
I think it's not working.
I think the inner orbit planet is move more faster
Right?
because of the formula we in the article, and can I show the
And you just tell us all the pattern you can see
all the pattern we can see and
from this.
from this.
Right. The first is the inner planets spin around the sun faster than the outer one, right? Okay, what's next?
Next one is their orbit is like circle or like the orbit.
Alright,
Like-
and do you think it's normal to see 10 balls like this?
Random.
Yeah.
If the sun becomes a random ball, I don't think it has enough properties to maintain the solar system. So, so planning will.
Right, what else can you see from the video?
Planet behind the cross lines here.
Well, it's not related to the movement. I'm asking about the movement. Right. All right. Students, answer from you. What are the peculiarity in their movements? Hank,
The 9 balls are rotated in one ball.
in what?
In that one ball. I think
Rotate
it's
around.
this.
And
And
in addition to that, when they rotate, is there anything special around the ball, the central ball?
I think the random ball is with that.
Right.
So I think the difference between random and this is the gravity, and that's a big difference.
Okay, they rotate around this ball. Anyone want to elaborate on that? Okay, Ethan.
They rotate the same way.
Same way means which way?
Which is the
Counterclockwise.
clockwise, and they have their own orbit. They will not cross each other.
Co-planar. Right.
And they are in the planet. They are 共平面.
Yeah, Yeah, coplanar. That's what I meant. Okay, and their orbit does not cross each other. That's also right. So, as Ethan elaborated, they are coplanar. Their orbits. Their orbits. I think most of them do not. The orbit do not cross each other, and they all rotate in the same counterclockwise way. So when you think about this, it's absolutely strange. This will not happen with 10 random balls, like you go to the table game, table ball, and you play and they don't move like this. So, and this will actually tell us about the evolution of the solar system. Okay, so Ray, thank you. Okay, well, shout out. So we will talk about the planetary system today. And happily, this will be our last week of Geochemistry. I think you are already saturated. So where have we been? We talked about Big Bang for the first week, and then we talked about for the past 2 weeks element formation by nuclear fusion, by R process, and also by S process. That's what we have learned. And then so far by talking about the stellar evolution, 星星的演化, we talk about the death of stars. But we did not talk about the birth of stars. And 2 weeks ago in the video, the video actually talked about the birth of stars. And this is actually the topic today. Where are we going? What happens when remnants? Remnant is whatever is left. 残余物 of supernova explosion cool down. And from the observation of astronomers, we know that in the remnants there are already molecules. Because so far in this class we only talk about elements. We did not talk about molecules. But actually in the supernova, in the explosion remnants, there are molecules. And of course, question is which one? And we also know that there are materials in the form of dust, ice, and gas. That's astronomers know. And how does the planetary system form between this and from the remnants of supernova explosion? So here we will shortly talk about molecule formation. It's a little bit boring here. Here, as I repeatedly say, if you want chemical reaction, you need low temperature. If you need nuclear reaction, you need high temperature. And in stars, we have very high temperature. And therefore, we have nuclear reaction, and in stars, the so-called state of matter is plasma. This word is probably strange to you. But actually, if any of you study metal, for example, if you are in 简国彤老师 lab, you will probably heard an instrument called ICP mass. ICP mass, P in ICP means plasma. In Chinese, we call this 电浆. So that's a very weird concept for you because you don't see that often on Earth. But actually, plasma is the most common state of matter, 物质相, in the universe because that's the major state of matter in stars. So, plasma is the so-called fourth state of matter. Usually when we talk about the state of matter, we use the temperature and pressure diagram. And actually, the so-called pressure is equal to number density, which is the number of particles per volume. That is pressure. And so this is equal to pressure. And here, this is temperature. So you see, the states of matter that we are familiar with, like solids, liquids, gases, they are here. They are only at a very small corner of all of the possible PT diagram. And the major state of matter is here. They are actually different kinds of expression of plasma. Like, for example, solar wind, like Ray just mentioned, is also plasma. And another thing you will see on Earth is lightning. It's also plasma. Okay, so plasma is the major kind of state of matter in the star, and is actually charged. It's actually elements with the outer electron strike off. But it's different from ion. You say, okay, in seawater we also have a lot of ions with probably one electron less or one electron more. But the difference between plasma and ion is plasma exists only at very high temperature and very low pressure. Very low pressure. So, under these circumstances, this kind of charged particle is no longer an ion. It's plasma. Okay. More about plasma. Plasma is ionized gases where the elements are stripped of their electrons, and is a chaotic mixture of ionized nuclei and electrons. It's the most common state of matter in the universe. It's observable on Earth through the solar aurora, 日冕, the northern lights, 极光, neon, 霓虹灯, and lens, or yen. The analytical principle inductively coupled plasma mass spectrometry, in short, ICP mass, is a popular instrument for trace metal analysis, and it actually converts your sample into plasma and analyze the plasma. So you sometimes you see plasma in your lab. Okay, I stop here, and we come back 11 after 11.